Have you ever wondered how you could teach a machine to do more than just see data, but to actually understand its very essence? You know, to learn the fundamental patterns of a face or a piece of music so well that it could not only recognize it, but create a brand new one from scratch. Well, that's the journey we're going on today. Okay, so let's get right into it. What we're asking a machine to do here is to go way beyond simple memorization. We want it to learn a compressed, really meaningful representation of data. And then, this is the cool part, use that understanding to generate completely new examples. And the tool that gets us there is a fascinating type of neural network called an autoencoder. At its heart, an autoencoder is trained on a task that sounds almost useless. Its job is to copy its input to its output. That's it. But here's the catch. We deliberately build it so it can't copy perfectly. And that constraint, that little bottleneck, is what forces it to learn something incredibly useful about the data's structure along the way. So to really get how this works, we need to look at the basic architecture that pretty much all autoencoders share. And it's a beautifully simple two-part system. So what you're seeing here is the whole blueprint. On one side, you have the encoder. Its only job is to take a big, high-dimensional input, like a full image, and squash it down into a much smaller, denser representation. We call this the code. Then, on the other side, you've got the decoder, which does the exact opposite. It takes that tiny, compressed code and tries its best to rebuild the original image from it. Let's just trace the data's path for a second. It starts as your input, gets squeezed by the encoder into that compact code inside the bottleneck. And then the decoder takes that code and tries to reconstruct the original. The whole system, from start to finish, learns together. And that bottleneck, that is the absolute key to everything. By forcing all that data through a representation that has way fewer dimensions than the original input, we make it impossible for the network to just memorize pixel values. It has to learn an efficient encoding. It's forced to figure out what the most important, the most salient features are. This is what an undercomplete autoencoder is all about. It learns to shrink data as a side effect of just trying to copy it. So, this brings us to the network's main goal, minimizing what we call reconstruction loss. You can just think of it as a penalty. The model gets penalized every single time its reconstructed copy is different from the original input. The entire training process is just a constant push to get that penalty, that difference, as close to zero as possible. But you know, a problem comes up if you give an autoencoder too much power, like a really big bottleneck or super strong encoder and decoder networks. It can find a loophole. It can learn to be a lazy copy machine. So let's see how we fix that. Exactly. If the autoencoder can perfectly copy the input, it never actually has to learn anything meaningful about the data itself. It just learns a function that perfectly reverses itself, which, for our goal of understanding the essence of the data, is completely useless. The solution to this is just wonderfully clever. Instead of asking the network to just copy the input, we change the rules. We give it a corrupted, noisy version of the data, and we ask it to reconstruct the original, clean version. This forces the model to learn the real underlying structure, not just memorize some pixel patterns. So how does this actually work? Well, we start with our clean input, the original data. Then we deliberately mess it up. We add digital noise, or maybe we just blank out parts of it. This corrupted version is what we actually feed into the autoencoder. The Denoising Autoencoder, or DAE, now has a much harder job. It has to undo all that damage. It can't just copy the input anymore. It's forced to learn what a 7 fundamentally looks like so it can fill in the missing pieces and get rid of the noise, spinning out the clean image on the other side. It learns robust representations because it has to learn to see through the mess. Learning robust features is a huge step up, for sure. But what about our original goal of creating something new? To do that, we need to take a probabilistic leap. We need to move from a deterministic autoencoder to a generative one. So here's the key issue with standard autoencoders: their internal map of the data, that latent space. It's often messy and discontinuous. It's full of gaps and empty regions, and if you try to generate a new image from one of those gaps, the decoder just produces nonsense. The Variational Autoencoder, or VAE, fixes this by forcing that latent space to be smooth and continuous, making every single point meaningful. It's perfect for generation. So how does a VAE build this nice, smooth space? Well, instead of mapping an input to a single, precise point on the map, its encoder maps it to a probability distribution. Basically a fuzzy region, defined by a center and a size. It's saying an image like this lives somewhere around here. This probabilistic twist is the key that changes everything. A VAE is trained with this really cool dual objective. You can imagine it as a tug of war between two forces. First, you've got the reconstruction loss, let's call it the forger, which just wants to make the final copies as accurate as possible. But then you have the second component, the KL divergence, which acts like the librarian. Its job is to keep the whole map organized, forcing all these fuzzy regions to be nicely packed together, which prevents those gaps we were talking about. And this organized, probabilistic latent space is what finally unlocks the autoencoder's generative power. It's not just a compression tool anymore, it's a creative one. And the result of this whole process is a beautifully organized map in that latent space. The VAE literally learns to cluster similar data points together in a really meaningful way. All the different ways you can write the number 1 find a home in one neighborhood, while all the zeros cluster together in another. It creates this smooth, totally navigatable space of ideas. And this is where the magic happens. Because this map is continuous, we can pick a point from anywhere on it, even from a spot right between two-digit clusters, and we can feed that new code to the decoder. And what does the decoder do? It generates an entirely new, realistic sample that corresponds to that point. We're no longer just reconstructing things we've already seen. We are now creating novel data from scratch. So let's just quickly recap our journey here. We started with a basic autoencoder that learned compression by just trying to copy things. We made it smarter by creating the Denoising Autoencoder, which learned robust features by fixing messes. And finally, we arrived at the Variational Autoencoder, which learned a probabilistic map of the data's essence, letting us generate entirely new creations. It's a pretty powerful evolution, right? From simple copying to complex creation. This journey really shows the incredible potential we've unlocked. The question isn't just, can an AI understand the world anymore? It's, now that it can learn the fundamental essence of things, what new images, what new sounds, and what new ideas should we ask it to dream up for us?